Welcome back everybody to another video lecture from Miss Semino. On this part of the video we're going to go ahead and be discussing the light equations. So we'll be making some calculations as well as describing the different parts of the wave and a little bit more about the quantum mechanical model. In the second part we'll go ahead and be discussing the atomic spectra. We're going to go ahead and be talking about the relationship between wavelength and frequency, identifying the sources of atomic emission spectra, and then explaining how frequencies of emitted light are related to changes in electron energies. This sounds really kind of confusing, but it's really just going to revolve around two equations this evening. So to start off with, we need to go ahead and talk about some facts about light. So first off, the study of light led to the development of the quantum mechanical model. So remember we were talking about the electron's address and where they're located. In addition, light is a type of electromagnetic radiation. You might have heard this term before, electromagnetic radiation. It includes light, but it also includes other types such as gamma rays, X-rays, and radio waves. When we talk about light, sometimes we'll talk about the speed of light. This is a variable abbreviated with c, and the value that it goes along with this is 2.998 times 10 to the 8th. So I was just about to say 3, and that's because we'll often see on our worksheets that the speed of light is referred to as 3.00 times 10 to the 8th meters per second. So you can see either one of these on your worksheets, and this should be like a 10 to the 8th here. Or 3.00, because you could see if you take this and you round it up, you're going to get your 3.00 times 10 to the 8th meters per second. In addition, all electromagnetic radiation travels at the same rate when measured in a vacuum. So when we talk about the speed of light, we can also be talking about the speed of electromagnetic radiation, and so that speed is going to be this 3.00 times 10 to the 8th. So let me apologize by saying that this slide is going to take us a long time to talk about. There's a lot of really good information on here. So first off, we'd said that light is part of the electromagnetic spectrum. So you can see visible lights down here, but it also has radio waves, radar, microwaves, infrared, ultraviolet, X-rays, and gamma rays. Okay, so this is the electromagnetic spectrum, which visible light is part of. When we talk about the electromagnetic radiation, there's things that we can calculate and need to know about. The first thing is the wavelength. I think this is easy. So when we talk about wavelength, we're talking about like from distance from one peak to another peak. So as we go across here, we can see that the wavelength is getting shorter and shorter and shorter and shorter. And you can also see that by just looking at the pictures, but hopefully if you look at the distance down here, we can see that we have 10 to the second wavelength, a wavelength of 1. And remember, this is going to be measured in meters down here. We have a wavelength of 10 to the negative 2, so the wavelength is progressively getting smaller. And so, by the way, I want to mention this little symbol down here. It kind of looks like a little A thing. That is the symbol for a wavelength that we'll see in the equations in a second. Opposite over here, we've got frequency. So notice that frequency actually is increasing as your wavelength gets smaller. And so remember when we talk about frequency, that's how many times this peak reaches per second. So if we are kind of continually going through something, okay, so if we had a wavelength here, we have this distance here. If we had a wavelength that was like this, you can see that there's more peaks per that same area, so the frequency is higher in this second drawing down here, which is not a very good drawing, but hopefully you can see like there's more peaks here, so over this given distance we have more frequency of waves, we have less frequency of waves here, but on the top we have a longer wavelength, on the bottom we have a shorter wavelength. Okay, so on that last slide I was talking about a couple of terms. You might be like, I have no idea what she was talking about. So let's go ahead and talk about the parts of a wave. So this top part of the wave is called the crest, or sometimes I'm going to call it the peak. This distance from peak to peak is called the wavelength. You might want to know this bottom's called a trough. I'm not too freaked out about that. But the amplitude is the distance here from the origin, which is like this line that goes evenly through this wavelength, to the peak or the crest there. So when we're talking about wavelength, I want you to be familiar with these two wavelengths. First off, at 400 nanometers, sorry, it's kind of written weird on this slide, we have violet. So violet has a shorter wavelength than red does. Red starts off with a wavelength of about 750 nanometers, and so red has a longer wavelength, violet has a shorter wavelength when we're talking about the visible light spectrum. So I like this picture here. On the top here, we can see that we've got a longer wavelength, but we have a low frequency. On the other hand, we have a smaller wavelength here, but we have a higher frequency. Again, the number of peaks per like this given distance. So here we have a few factoids with wavelength and frequency. First, these two things are inversely proportional. As one goes up, the other one's going to go down, as we saw in the picture. Different frequencies of light give different colors of light. So I mentioned that violet has about 400 nanometer wavelength, while red has 750 nanometer wavelength. There's a wide variety of frequencies, and this whole thing is called a spectrum, or the electromagnetic spectrum. So here's the equation that all this information was leading up to. It's first off that c, or the speed of light, is equal to lambda times nu, and that's what those funny symbols are. I think this lambda kind of looks like an A without the thing across it, and this one looks like a V to me. So the lambda here is representing wavelength, and the nu here is representing the frequency. So here on this slide we have a sample problem for us to go ahead and calculate. It says calculate the wavelength of the yellow light emitted by the sodium lamp shown above if the frequency of the radiation is 5.10 times 10 to the 14th hertz. We really haven't talked too much about hertz, but the idea here is that hertz, oops, let me see if I can write that better. Hertz is equal to 1 over s. So it's just another way of saying like s to the minus 1, which you've seen before. So all of these are equal to each other. So if we want to go ahead and solve this problem, we're going to go ahead, and I always like to write my equation first. So our equation is c equals lambda nu. And in this case, we're looking for the wavelength, so we're looking for this one. So we want to go ahead and divide both sides by the nu, or by the v. And so you can see that the v's are canceling over here. So our speed of light, we're going to divide by our frequency to get our wavelength. So at this point, we can go ahead and plug in our values. You can see that they're giving us this value for speed of light. So if they give you a specific value, you want to make sure that you're using that. So I'm going to go, sorry, that's a 2.998 times 10 to the 8th meters per second, divided by our frequency, which is the 5.10 times 10 to the 14th hertz, or 1 over s. Okay, so this is going to be 1 over s. So hopefully you can see that both of these s's are on the bottom, and so we are going to be left in meters, which makes sense because that's what we want our wavelength to be. And we'll just go ahead and just plug this into our calculator and get our answer this way.